Okay, Assalamualaikum and good morning, guys. Okay, so this week we continue with the revisions for the test one. Okay, so please refer to 2014-15 test one paper. Can you hear me, Kon Yawen? Kon Yawen, can you hear me?
Yes, Doctor.
Okay, can you read question one, please?
Closed loop system in figure Q1 has the following open loop transfer function. From the root locus of the system, the dominant pole of S -2 plus minus J4.46 yield a value of gain K with natural frequency 4.89 radian per second. A, sketch a root locus shape of the closed loop system. B, determine the damping ratio of the system. C, find the setting time, peak time, and percentage overshoot for the given damping ratio in B. D, validate the second order approximation of the system. E, sketch the estimated second order closed loop step response from the information obtained in C.
Okay, thank you very much. So let's go to the solutions. Okay. Going to the iPad. Okay. So this is the questions. So by looking at this, is the third order system. System type is 0. So 3 open loop poles, meaning that 3 root locus paths. Okay, no zeros. So the root locus is not given, but the dominant pole is given here. Okay. And omega n is given, right? Okay. So how are we going to do it? Is by writing the details, okay? Which is the open loop transfer functions. That's 10. Then find the closed loop, which is the key again. S plus 1 plus K. Okay. So given the closed loop dominant pole by -2 plus minus J 4.46 and omega n 4.89 radian per second. So when we sketch the root locus, okay, so we have 3 open loop poles, which is given by -1, correct, -6, and -10. Okay. So what is the expected root locus path? So we start from the origin, no poles, no zeros. Then we met -1 poles. Then we move again to the left and -6. So automatically root locus by the concept start from poles ended at zeros or infinity. So since no zeros, so we suspect that there is one breakaway point. Okay. So this one is ended at infinity. And this one is a breakaway point. And then between -6 and -10, there is no root locus path, but -10 towards infinity, there is one root locus path ended at infinity as well. Okay. So it's given that this one dominant poles, okay, is given by this, right? So we know that dominant pole is start from 0 like that. Okay, so this is the dominant pole. But we don't know what is the zeta value. So how are we going to find the zeta value and the theta value? Yuvarajan, can you give idea how to find theta value and zeta value? Yuvarajan, not absent. No, Aina, Wahida, how to find the theta value from here?
I have the data value from the formula.
Sorry, cakap kuat sikit.
Formula Newton.
From the
Tapi
U-turn.
tak ada.
Zeta is not given.
Maybe from the graph.
From the graph. Graph also not given. Okay, Mukri.
Yes, sir.
How to find the zeta and theta value?
Theta using inverse tangent.
Inverse tangent.
And zeta, I'm not sure.
Kau ni je ingat tahu jawapan. Ni.
Yes, Prof.
How to find theta from here?
Theta inverse tangent 4.46/2.
Berapa?
Berapa? Sekejap.
65.85.
Huh?
65.85 degree.
So therefore, cos theta is what? Ni.
Cos zeta is 0.409.
Huh?
Yeah, 41.
0.09?
0.409. So
Oh.
0.41 betul.
0.41. Okay, thank you. Right. So that's how we calculate the theta and zeta. Okay, so what is the question actually? Sketch the root locus. Okay, sudah. Determine the damping ratio. So sudah. Settle. Find the settling time, peak time, and percentage overshoot for the given damping ratio in B. So this one is straightforward. 4 divided by real. Real part is 2. Excuse me. Peak time is pi divided by imaginary. So pi divided by what is the imaginary value? So 4.46. 0.7. Okay. And overshoot is using the zeta value here. Exponent by zeta. 1 minus zeta square multiplied by 100. So insert zeta 0.41 inside the formula, then you will get the OS at 24.5%. Okay.
Prof.
Boleh?
Prof.
Yep.
Yang
Dengar, kuat sikit.
yang tan inverse to 4.46 divided by 2 is the real number.
Ya,
Oh, atas ni menjadi okay.
sini. Nampak?
Okay, faham.
That's why you kena buat revision. Kalau tak nanti you will lost lah during test 1 blackout.
Thank you, Prof.
Right. Welcome. Okay, so settle this one. Validate the second order approximations. How are we going to carry out this? First is you have to find the k value first. Okay. Find the k value first. Ismail. Akhi.
Yes, doctor.
What is the k value at the dominant pole?
We insert the pole magnitude criteria
as written by me. Okay. So you insert the value, which is -2 plus j 4.46. You insert inside the gain criteria, okay, magnitude criteria. Then you will get the k value is 250. And then from the characteristic equations, okay, so the characteristic equation just now is this one. This one, equal to 0. So s plus 1, s plus 6, s plus 10, right? S plus 1, s plus 6, s plus 10 plus k equal to 0. Okay. So this one you simplify. Okay. S square plus 7s plus 6, s plus 10 plus k. Simplify again. S cubic 7 s square plus 70s plus 6s plus 60 plus k equal to 0. Simplify, so you will get s cubic 17 70s 76s 60 plus k, but k is equal to 250. So insert k inside there. $250 plus 60, so it is 310, correct? Is mine.
Yes.
And the roots?
Negative 12.98.
Negative 12.98. The remaining two? We have 3 cubic.
Yes, negative 2 plus minus 4.46 or 4.45.
Inshallah. So this one is dominant pole, okay? A pair of dominant pole, right? And this one, the blue one, is the that pole, okay? So what is the name of the rules that we're going to make second order approximations. May I ask Snawi, what is the rule we use to apply second order approximations?
Tak ingat tu.
Astaghfirullahaladzim. Rule of thumb, i.e. ratio tadpole divide by real part. So what is the ratio? 12.98. Mas Nawi? 12.98. Mas Nawi, betul? Divide by 2 apa?
Betul.
Ya, berapa? Divide by 2.
6.49.
6.49. Which is
6.49.
greater than 5. Which is greater than 5. So rule of thumb said when the ratio is greater than 5, so second order approximations is valid or not valid? Yuki Wong? Valid or not valid?
Valid.
Valid, eh? Okay. Understand? And then sketch the estimated second order closed-loop step response from the information obtained in C. Okay, but we have to calculate the error first, lah. Okay? So TS is 2 seconds. TP is 0.75 seconds. Overshoot is 24.5. Kau Holiong, can you off your microphone, please? Thank you. Okay, so system type 0, so we use KP. Okay, so KP is Leong. KP is limit S to 0. Okay, KGS. So limit S to 0, 250 over S plus 1, S plus 6, S plus 10. So KP is equal to 4.2, 250, 1 multiplied by 6 multiplied by 10, so 4.2. Okay. So what is the steady state error? Chung Hui. Chung Hui. Absent. Sami, what is the steady state error?
1/1 plus KP,
Okay.
which is 0.19.
So therefore the plot is like this, time response. So this is the input. Okay. And the output is something like this. Okay, 0.1. Okay. Where this is 24.5% overshoots. Okay, peak time 0.75. Settling time somewhere here, 2 seconds. And the error is here, 0.19. Khalas. Sammy? Khalas. Okay, understand?
Yes, doctor.
Alhamdulillah. Alhamdulillah. Shukran. Right, so
Doctor, I have a question regarding finding the value of K.
okay,
Could
all
we
right.
have also used the Ruth-Witts table?
To find the key for Ruth-Lewis table, no need, because if you use Ruth-Lewis table, we usually want to find the K critical. Okay, so you use Ruth-Lewis table when the like this. Okay, so you want to find this gain K critical. Okay, so you have to use a Ruth-Lewis table. But if you want to find K at the dominant pole, you just use this formula. Okay, this formula, magnitude criteria, insert the value S inside, and then you get the 250. Okay.
Yes, doctor. Thank you.
Fahim tak? Alhamdulillah. Right, any question, guys? Question, no question. If no question, we move to question number 2. Chong Juan,
Yes, doctor.
can you read question number 2? Kuat sikit suara. Volume
Okay.
speaker.
Figure Q2 shows a root locus of unity feedback system with the forward transfer function as follow. GS. The system operates at a damping ratio of 0.4472. A. Determine the gain K and the dominant poles for this system at the required damping ratio. B. Estimate the settling time, peak time, and steady error for the value of K in A. C. Design a suitable compensator that could reduce the steady state error to 0 without affecting the system transient response. D. If the dominant poles of the required system is S equals to negative 0.66 plus minus J 1.33, after the new compensator is added in C, find the value of the new K, the proportional gain Kp, and the integral gain Kt.
Okay.
The new peak time,
Yeah.
the new peak time, settling time, and steady state error. The third, sketch the uncompensated and compensated responses, show all important values for comparison purpose. Comment on the results obtained after the compensator is added.
Sure. Yeah, thank you very much. Okay. So the plot is given here. Okay. It is a third order system. Okay. Third order because S cubic. Okay. And we have a complex conjugate poles. Okay. Complex conjugate zeros as well. Okay. CCP, CCZ. And then the system is type 0. Okay. Because there is no poles at the origin. So this is the plot. So the plot is start from the poles ended at zeros, and the last one ended at infinity. Right, so let's go. Question number 2. So yes, open loop transfer functions. Okay, and the closed loop transfer functions. Okay. So by looking at the plot here, So zeta for 0.4472. So how are we going to draw and to find the dominant poles? Natra?
Yes, Doctor.
Tak dengar semua. Kuat sikit.
Yes, Doctor.
How are we going to find dominant pole? Dominant pole from zeta value given.
I use protector.
Find the degree first.
Draw zeta lines and find the
Berapa? Berapa? That's right.
Zero. 63.
60.
Point 44.
Okay. So now, how are you going to plot? We don't have any printer.
Use protector.
Use protector. Then, how you put the protector on the plot?
Put
Ada printer? You have printer?
protector and put on the graph and make sure it at the origin.
You have printer?
Yes, I have.
Okay, you print this one, okay? You print, then like that, okay? So zeta is 0.44. Okay. So this is the dominant pole. So the dominant pole is minus 0.67 plus J 1.34. Okay.
Excuse me, Doctor.
Yeah.
If we use a protractor, if we get a slightly different number, because I'm not sure if we can get 6-7 to the second decimal place, will it still be okay?
What do you get?
Like if it's not to the second decimal number, if you got 0.7 only,
okay,
will it affect the answer that much?
Halal, inshallah, accepted.
Inshallah. Thank you, Doctor.
Small value, okay, but if you get 67 plus 13.4, this one is wrong.
Yeah, it's too far away.
Too far away, not too far away, okay? No worries about that, okay? It's open, okay? Right, and then, so we got the dominant poles. Which is minus 0.67. Okay, and then we want to find the key here. Okay, we want to find the key there. So how are you going to do that? Sharif Hafiz Ali?
Yes, sir.
How to find key?
Insert the value of the dominant poles into the characteristic equation.
Insert to where?
To the characteristic equation.
Characteristic equation? No, you don't understand that one.
Insert the denominator, but I don't know what is the terms for it.
Tak cukup ulang kaji. Besok exam ni. Wan, tolong ni Wan. Berapa jawapan? How to find K at the dominant pole? Wan?
Ya, Doktor.
Saya ke tak?
Muhammad Alimi.
Ya, Doktor.
How to find K at the dominant pole? Tak tahu. Allah. Si Micin?
Hi, Doctor. Using the GS, 1 per GS, and then substitute the S.
So the equation is?
Absolute s squared plus 2s plus 2 times s plus 4 over s squared minus 2s plus 8.
Syarif. Syarif.
My mistake dia.
Ni.
Modulus. Okay.
Astagfirullahaladzim. Tak study lagi ke?
Dah, tapi salah lah ni.
Faham lagi. Aduh. Penat lah.
Kena banyakkan lagi lah kata.
Banyakkan lagi. Kan? Banyakkan latihan lagi. Jangan give up pada masa lagi. Baiki diri. So when you insert the value, use calculator. So you will get 0.436. Okay? Set this one. Natra, faham tak? Natra.
Faham tak?
Faham I see you today. Faham Alright, this one done. Damping ratio sudah. Settling time. This one easy. Just insert the value. Okay. Settling time. Yes. Okay. So the system is type 1. What is KP value? It's type 1. Type 0. What is KP value? Abdul Rahman Ludin. Abdul Rahman Ludin. Absent. Ivan.
Zero 0.436 times GS.
GS,
GS.
Oh, where are you? Shopping complex. Okay. So KP is 0.436. Same like the gain because it's cancel out each other. Okay, and the steady state error will be Denson.
One over 1 plus KP.
.7. Okay. Okay. If the dominant pulse of the recovered system is 0.66 plus J 1.33 after the new compensator is added in C. Design a suitable compensator that reduces the steady state error to 0 without affecting. So what controller we should use in C? Tika. What controller we should use in C? P ke, PID ke, PD ke? Tika tak datang.
PD.
PD, astagfirullahaladzim.
PI.
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 PI controller. Okay. So the answer is use PI controller that can reduce the steady state error. Okay. System PSS 0.7, quite big. And to reduce ESS to 0, comma, use PI controller. Okay. So what is the PI controller that you suggest for this? Con Yawen.
I'm not sure.
I'm not sure pula. I'm not sure pula. Allah Akbar. Nur Hazika Shazwina. Suggest PI controller bah. PI controller bah. Suggest lah. Senang aja bah.
Don't know.
Huh? Don't know. Don't know is not controller. Astaghfirullahaladzim. Wenjin. Suggest a PI controller. Not sure. Ayo. K S plus 0.1 over S. That's all. Very easy. Don't make life complicated, guys. S plus Ki over P divided by S. Okay. Okay. Aduh. Aduh. Okay. That's all. Just suggest. If you want to suggest 0.01 also can. Okay. 0.5 also can. Okay. Any small number that is near to the origin. Boleh? Benjin? Okay, Ma? Hah? Tak dengar lah. Kuat sikit. Speaker tak kuat. So if the dominant pole, okay, so C, so you is given like this after you apply PI controller. Find the new value of new K, okay, the proportional gain, KP and KI. Okay, so how are you going to do that? How are you going to do that? So the concept is here, if you look here, mana tadi? Ni kan? Okay. KP itu is equal to K lah kan? Okay. So GPI tadi itu sama dengan KP equal to S plus KI over KP divided by S. Okay. So first you have to find the K first. Okay. So the K is from the formula with the PI controller. Okay. So in this case, you have to find the 1 over GS tadi itu, plus 8. Then S plus 0.1 magnitude. Okay, and then S, the integral, then the zeros, 2S plus 2. Integral, then S plus 4. Balik pula, balik kot. S plus 0.1. No, balik. So you have to do like this. And the K value, padam. Okay. Usually it starts from the macam ni. So GPI kan. So it will be like this. S square minus 2s plus 8. Okay. S square plus 2s plus 2s plus 4. Then the PI, the PI is s plus 0.1 divided by s. Okay. So in order to find the k is magnitude 1 over GPI. Magnitude. So the denominator will go up. S square plus 2s plus 2 s plus 4 s divided by s square minus 2s plus 8 s plus 0.1. Okay, magnitude. Okay, then replace with the value given, which is what tadi? 0.66 plus j 1.33 given. Okay, inside k. Okay, so that's why you will get k is 0.445, which is equal to kp. But we know that ki over kp that we defined just now is equal to 0.1. So that's why ki is equal to 0.1 minus kp, which is 0.0445. Okay. Okay. The new peak time, the new settling time, and the new steady state error. So again, so when you apply for the new one, after you insert PI controller, so TP will be pi divided by 1.33, 2.36 seconds. Settling time is 4 divided by 0.66, the real part given, which is 6.1 seconds. And the KP now, have to recalculate again. Limit s to 0, okay. GPI, okay. So KP, limit s to 0. The gain is 0.445, okay. Then s plus 0.1 is the zeros at the origin. Then s square minus 2s plus 8, complex conjugate zeros. Integrals, complex conjugate poles, and poles at -4. Okay, so when you insert that, so it will be infinity. Okay, so the error will be Zareth. Steady state error will be
infinity.
Astaghfirullah. 0 mah. 0, 1 over infinity. Zareth. Oh, Zareth.
Yes, sir.
1 over 40 billion. How much? 1 over 40 billion.
0.
0.000. Okay. Something lah, eh? So 0, 1 over infinity. Check it out. This question is actually very good. They're very deep and detailed. Sketch the uncompensated and compensated response. Show all the important values. Okay. So can you sketch? Can you sketch? Okay. T input 1.0. Okay. Before, this before PI and after PI. Okay, like this. Liana, Camelia.
Yes, bro.
You understand?
Oh, yes, understand.
Any question?
Excuse me, doctor. I have two short questions.
Yeah, sure.
For the test, we have just to show just a mere sketch like that, or we have to like label it with the TPTS.
Oh, you sketch and label lah. Better you sketch and label.
And label. Okay, doctor.
Without label, so the lecturer that mark the test will not understand what are you trying to inform.
Okay, doctor. Doctor, my second part of the question is for the before PI.
Before, okay.
Before PI, should the TP be above 1.0 or it's also below?
The TP just now is 2.36 second. This is after PI. Before it is 5.997 seconds. Okay, so a little bit faster lah, a little bit faster.
Yes, okay.
Because this one is a freehand draw, so if you draw like this is also okay, no problem. Okay.
All right. Doctor, for when
a little bit to the left. Okay.
Yeah. Doctor, just one last question. For when we found K for the GGPI, why did we reverse it? Like, why is the numerator denominator numerator?
Because it's 1 over G. 1 over G GPI. Okay.
Oh, okay.
That's why you see that the denominator part at the bottom, at the top, and numerator part at the bottom.
Yes, yes.
Okay. Okay.
Thank you.
All right. Shukran. Any questions before we break for 10 minutes? Soalan. Faris, any question?
No question.
No question, eh? Omar, any question?
No, doctor.
Okay, so we have a break for 10 minutes. Is it okay? Okay, 10 minutes break. Okay, guys, we continue the second part of the revisions. So I invite Patrick. Can you read the questions? Hello, Patrick. Are you there?
Yes, doctor.
Okay. Question 1, please.
Okay. Question 1. Closed loop system in figure Q1. A has the following open loop transfer function. GS equal to K over S plus 2, X squared plus 14S plus 53. So the root rockers of the system is given in figure Q1B. prove that S equal to -8 plus J 3.2 is also one of the closed loop poles. B, calculate the gain K when a closed loop poles are at the breakaway point S equal to -0.85 and the J omega closing S equal to J 2.5. And C, hence determine the range of K for the system to be in overdamped, critically damped, underdamped, and undamped condition, assuming that the system can be considered as a second order system. So the last part D, if a 0 is added at S equal to -7, sketch the new root locus for the system.
Thank you. So this question plot is given as usual. If you have a printer, print it. Okay. Or if you don't have a printer, you can ask your friends to duplicate some copies. Okay. Right. So this is the questions. Right. Okay. So we can extract some info here. Is the fourth order system. Okay. S4 is a type 1, correct? Because we have a S over here. So you use KV, velocity error constants. And we have 4 open loop poles. So 4 root locus paths. Okay. What else? Okay, that's all. So prove that -8 plus J is also one of the closed loop poles. How are we going to prove this one is equal to -8 plus J 3.2? Okay. 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 So we how are we going to check whether that point is a root locus point? So we use what tools? Nur Safwana? Datang.
Yes, Prof.
Nak panggil. How to prove this point? Use what? Use angle criterion. Okay. So what is the angle criterion formula? Which is this one. Seven plus J2. Okay. So you have to find the roots of this. Okay, the roots is minus J plus minus J2. That is the roots for the complex conjugate poles. It's a quadratic roots. Then the angle of criteria is for the constant, for the gain, minus for the S, minus for the S, plus 2. S plus 1 or S plus 2? S plus 1 or S plus 2? S plus 2 then. S plus 2 eh? Then minus the angle of S plus 7. Okay. So we insert S equal to minus 8 plus J 3.2 inside here. Okay. So you will get angle criteria, okay, which is minus K minus minus 8 plus J 3.2, okay, then plus minus 8 minus, you insert inside because it's quite long, so I takes time to copy, okay. So you insert this value, okay, inside that, and then you find the angle. So the angle is 0 degrees because of the gain. Gain is 0 degrees minus 158.2 degrees, 151.9 degrees plus 100.88 degrees plus 129.8 degrees. Okay, so the angle is minus 540.78 is about 3 times minus 180 degrees. So proven minus 8 plus J 3.2 on root locus. Okay, because it fulfilled the angle criteria. Calculate again when the closed loop poles at breakaway point 0.85 and J omega crashing J.2.5. So here the breakaway point, and here the omega D. Okay. Okay. So you have to calculate the gain at the breakaway point and K critical. Okay. I just want to ask you whether you understand or not. What is the value of zeta at breakaway point? Muhammad Tauri? Absent. Omar? Omar? What is the value of zeta at the breakaway point?
1.
Hmm? 1, yes. Critical depth. And Safwana, what is the zeta value over there? Ona? Zeta 0, which is a undamped. Okay, so now we calculate the corresponding gain. Okay, gain K at breakaway point. Okay, which is minus 0.85. How I get 0.85 is by reading from the graph given. Okay, So you have to read this point. So it is a minus 0.85. Reading from the graph paper given. So as usual, okay, so we use the formula for the magnitude criteria, which is S plus 2, S square plus 14S plus 53. Okay, so you insert inside. So you will get the K value at 40.9. Okay. Then what is the omega D point over here? Somebody please read for me. C Michin. What is the value of the root locus intersect with the imaginary axis?
2.6.
2.6. Okay, substitute from the schema is J 2.5. Okay.
Sorry.
It's okay. So 2.6 also okay. C Michin. Okay, the schema is 2.5. So you measure 2.6. Maybe your, your eyes is much accurate. Okay, so both can be used. So again, take the point there. But this time around, okay, again, K at intersection of RL and J omega, which is S is equal to plus J 2.5. Okay, so you use the criterion magnitude again, okay, which is just now. Okay. But you insert this value plus J 2.5, no real, okay, no real value, so no real part. This one, no imaginary part, is a real part, okay. This one is the imaginary part, no real part. Okay, so be careful when you insert. Then K will be 467.2. Okay. Understand? Understand, guys? Okay. Determine the range of K for the system in to be overdam, critical dam, underdam, and undam conditions, assuming that the system can be considered as a second order system. Okay, so this one, okay, just draw like this. Okay. 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 Okay, something like this. Okay, we already have the value over here. Okay. This one is zeta is equal to 0, zeta equal to 1. Okay. K critical. 467.2. This one is K, which is equal to 40.9. This one is minus is a J 2.5. And just now is the value is what is the value there just now? This one 0.8 minus 0.8. Okay. So the green zone, okay, the shaded green zone is the underdam region. Okay, which is okay, we call it the underdam region. Okay. This part is this part we know as zeta is less than 0. Okay, so zeta less than 0 is negative dam. Zeta between 0 and 1 is underdam. Zeta equal to 0 is undam. Zeta is equal to 1 is critical dam. Okay. So that is the C. Then when you added S equal to -7 to the root locus, what happened? So now the equation will become K 0, Ks plus 7, S plus 2, S square plus 14S plus 53. Okay, so I'm going to do the plotting again. Okay, this. Okay, then we have just now the value of zeros is berapa tadi? This one -7. Kan? 7. G2. And then you add 0, which is you add 0 over here. Okay. So what will happen to the plotting? Before you add 0 at 7, the plotting is shown here. This is the plotting. Okay. Sorry. So this is the plotting before you adding 0 and -7. So after you adding 0 over here, what happened to the plotting?
Do the poles go towards 0?
Yeah, that's right. By the concepts, okay, where root locus starts from poles and ended at 0 or infinity. So the plotting will be like this. Okay, especially 1 goes down and 1 goes up. Okay. So this one, Liana, Camelia? Liana, Camelia? Liana, Camelia?
Yes, bro.
Ni point apa? After we adding 0, so this point kita panggil apa? We call what? Break?
Breakaway point.
This one? This one? We call what? Break? Break in point. Faham juga. Liana? Boleh nak?
Yes, bro.
Baca soalan nombor 2.
A closed loop system is figure A. In figure Q2.8 has the following open loop transfer function. The root locus of the system is given in figure Q2b. At any value of k, the system can be approximated as a cycle of the system. A, find the closed loop dominant poles if damping ratio zeta is equal to 0.3. B, the system is required to have a peak time 1 second at the same damping ratio as in by A. Find the location of the new closed loop poles and design a PD controller so that the required peak time is achieved.
Right. Thank you very much. So again, we look into this is a third order system. Type 0. 3 open loop poles. Each 3 root locus paths. Okay. And the root locus is given. Okay, so see, it's given there.
Sorry, doctor.
Yeah.
Can you scroll up to the previous question?
The previous question, okay.
Yes. Scroll up, please, doctor.
Oh, one more.
Yes. C.
C.
No, not C. Yes, C. Should we like write the range of the K value for the overdamped, critically damped?
Yeah, also can. If you want to write a value, also can. If you want to draw like this, also can.
Okay. Thank you.
So, doctor, initially for the test, we can just do the same thing as you did, shade the regions and label them.
Yeah, the reason why I shaded the region because this region always asks in the past few exams questions. It seems that the coordinator like this region. I don't know why. It's a stable region, okay? So in between 0 and 1, okay? So you have a, 0, under dam, undam, critical dam, less than 0, negative dam, and the other one, over dam. So over dam usually in this region, okay? These are five locations of the zeta. So you must understand this, the one that I draw here. Okay, if you want to write like this, also can, no problem. But this one is much better because it visualizes where the locations of the closed loop poles.
Doctor, just one more question before we move on to the next question. Yeah. When you draw the new root locus, when we added the 0.7, the new 0,
okay.
How do we know that the shape is a concave?
Concave. Well, it depends on your understanding of this word. Okay, root locus start from poles and ended at zeros. This one actually on the first 2 poles, not much difference when you adding zeros and -7, but it really affect when you the zeros that near to the poles. Okay, so previously there is no zeros here. Okay, no zeros here. So the plotting is go up and go down. Suddenly you add 0 at here. So the 2 complex conjugate poles now in high alert because they have a friends there, zeros. Okay, and the zeros is correspond to this statement. So instead of ended at infinity, it will end it to the zeros, even though 1 is okay. Okay, 1 goes here, and the other one will be break in, okay, and goes to the infinity. So 1 goes to 0, 1 goes to the infinity. So fair enough. Okay.
Okay, doctor. Thank you.
And plus, you make more practice. That's why last week and this week I emphasize on the past year test 1 questions so that you can have the imaginations You know, when they ask like this, they ask you angle question like this, so you are well prepared for it. Okay, I hope, inshallah. I hope. Okay, and lastly, it depends on you how you answer the questions and how you write the questions. Okay, the answers for the questions. Okay. So question ni Lena kan, this one okay. At any value of k of the system can be at any value of k, the system can be approximated as a second order system. Okay, we know that the ratio is greater than 5. Okay. Find the closed loop dominant poles if damping is 0.3. Safana? Safana? Angle please. Soalan senang je.
Wait.
Jangan kecewakan saya.
72.54.
Berapa?
72.54 degree.
72.54
degree.
72. Okay. So as usual, print this plot, or if you don't have printer, Roger your friends. Okay, next room, next level, print this one copy. You pay lah, pay 50 cents or 1 ringgit, cost the effort, toner, inject, cost the value. So just like that. Zeta 0.3. Okay. So what is the dominant pole over there? See, Michin?
I think it's negative 0.8 plus 2.2. J. Oh, 2.4. Okay.
Sorry lah, 2.4. 2.2 also can. Okay. Okay, guys, understand? So find the closed loop dominant pole. Okay, finish. Then the system is required to have a peak time 1 second at the same damping ratio in part A. Okay. Right. So this is the new one, the new peak time. So what is the old peak time? Dominant pole. From here, peak time, old one. Berapa, Safwana? Pi divided by 2.4.
1.31.
1.31 seconds. But the new one is TP new, is 1 second. Okay, so much faster compared to the old one, right? Find the location of the new closed loop poles. All right. Okay, easy. Okay. So we want a new dominant pole. So TP new is 1 second. Which is equal to pi divided by omega d new. Okay. Which is pi divided by 1, 3.14. Okay. So the new real part is minus J 3.14. Okay. Then we know that omega D is omega n 1 minus zeta square. And okay, so zeta is 0.3. Okay, so therefore omega n mana? Berapa mana?
Three point
3.29. Is English Arab, ada Arab students. So the new real part so will be minus zeta omega n minus 0.3 minus 3.29 berapa? Mana? Siapa nak? 0.3 minus
negative 0.987.
0.987. Okay. So therefore, the new dominant pole is minus zeta omega n plus j omega d is okay, or more or less equal to 1. Okay, plus j 3.14. Okay. Okay. The new dominant pole. Okay, so design a PD controller so that the peak time is achieved at 1 second. Right. So what is the next step? What is the next step? Ni, what is the next step?
With the dominant poles, kata.
Ni dominant pole dia.
Plot.
Ni dominant pole dia. Dia suruh design PD controller. So what is the next step?
I don't remember lah.
Astaghfirullah. Berat ni. Oh, berat. Yuki Wang?
Yes, doctor.
What is the next step?
Not sure.
Not sure. I say man, I say not sure je. Bro, the ni lah, the explain.
False and zero.
Nak you want to measure the value of zeros kan? So what is the roots for this, Yuki Wang? Complex conjugate poles. Over here kan? Yuki.
Yeah. -1 plus -j 1.
Okay. 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 And where is the zeros? Okay, we locate the zeros. Let's see over here. Okay. Then, ni, after that,
Find the value zeros.
Angle lah.
Angle criteria.
Find the angle.
Find the angle using angle criteria.
Ini adalah theta z. Betul? So what is the angle criteria equations? Tika. Tika? Angle criteria equations. Theta 2
plus theta 3 minus theta z equals to 180.
Okay. So you measure theta 1. Theta 1 apa? Theta 1 Chung Hoi Ki. Theta 1.
Yes.
Theta 1.
Tangent. Inverse tangent. 1.
3.14 divided by
Over 9.
9 Okay, kirakan angle dia. Theta 2, Chong Juan, theta 2. Chong Juan.
3.14.
Theta 2. Chong Hoi Ki dia kira inverse tangent, awak kira theta 2.
Oh, okay.
Senang je theta 2.
1 over.
Theta 2 mah.
Oh.
Ini macam.
.14 inch.
Berapa? Chong? Chong Hoi Ki? Chong Hoi Ki? Berapa? Tangent. Hello? Inverse tangent 3.14 divided by 9. Chung Hoi Ki?
19.23.
Share. Chong Juan, 90 degree lah. Dan ada dua kan? Pairing tu. Okay. So the value of ZC 19.23 minus ZC, this is -1, this is 3.14. This is the new dominant pole. Okay, so x is equal to 3.14 divided by inverse tangent. Sorry, tangent. x-axis equals to 10. Okay. So that is the PD controller. So when you combine together, okay, so it cancel out. Okay, the zeros cancel out with the poles at -10. Okay, cancel out, and then the k, okay, at that particular point is so k, and k is 8.8 by insert the value of s is equal to -1 plus j 3.14. You insert this inside the k value, k formula. Okay, that is the KP and KD value. Alhamdulillah. Any question, guys? Any question? So we finished this part. So remaining is this one. 2016-17. Two 2017-18. And 2018-19. Okay, so we have another 3 to go. So before we end our session, so I would like to invite Okri. Are you there?
Yes, sir.
You read the question. Question 1.
2016, right?
Yeah, this one.
You're not sharing the screen.
Sorry. Yeah. Oh, sharing. Sorry.
A plant is controlled by a proportional controller K as shown in figure Q1. A, to construct the root locus for the system in figure Q1 with minimum calculation, some rules for sketching and refining can be used. By inspection, determine if these rules can be applied. Choose applicable A and non-applicable NA for your answer. State the reasons for your answers. B, sketch the root locus of the closed loop system. C, determine if a point -1 plus J1 is on the root locus. Give your reason. A point on the locus that gives dominant closed loop poles with zeta 0.7071 is -1.4 plus J1.4. Determine the required setting for the proportional controller K at this point. E, for the K obtained in part D, determine the system output response characteristics for a unit step input settling time, TS, peak time, TP, and percent overshoot. F, comment on the validity of the second order approximation based on the third pole location. Here you don't necessarily need to calculate the third pole.
Continue, question 2.
A, PI, and PD controllers are used to improve the performance of a system, give the general transfer function of each controllers and state the performance that can be improved by those controllers. B, the root locus for the closed loop. Atas kita. The root locus for the closed loop system in figure Q to A is shown in figure Q to B. The system operates at a damping ratio of 0.5. I determine the open loop transfer function of the system.
Determine, not determine.
Determine, estimate the controller gain K, the certain time, the peak time, and the steady state error for the system. It is important for the system to have zero steady state error while keeping the system to operate at the same overshoot. Is it possible to design a controller to replace the proportional gain controller K so that this specification is satisfied? Prove your answer. And last one, draw the complete compensated system block diagram, including the controller with the value of each proportional gain KP, integral gain KI, or derivative gain KD obtained, depending on your proposed controller.
Okay, thank you very much. So I think we end here. So we will continue on Wednesday. Is it okay? Is it okay, guys? Any questions?
No, bro. No, Doctor.
Okay, semua dah mengantuk. Okay, alright. Okay, thank you very much. So I see you on Wednesday, 12 p.m. Okay? Thank you very much.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank
Thank you,
you,
Doctor.
Thank you.
Thank you, Doctor.